Okay, so I'm going to talk about some fundamentals behind the evaluation strategies, irrespective of the building codes or standards that we use. So my first question, or first sort of important point to make, is why do we really need to evaluate the buildings and how this is done differently compared to the design of new buildings? So as you might have seen this presentation slide before, some of you, we rely on the building codes and standard to design the structures. And there's a reason why that is done because of the responsibility as well of the legal permission. We need to follow some standards or some codes for each country or each region. So these codes specify the requirements. They also give some acceptable solutions. What is acceptable, what system is accepted, what is not acceptable, and so on. And they also prescribe very detailed procedures, rules, limits, equations, and some tables and factors that we have to follow. Most of these are based on accumulated experience and a lot of testing and a lot of research, but not always rational. And I will explain to you why it's not completely rational. And one of the reasons is that they are trying to generalize for a large number of structures, for a large number of engineers, in a variety of conditions. So it's not always possible to be very specific, to be very detailed. So many things have to be rounded off, to be generalized and averaged out for this codes to be followed. But the spirit of the code is very clear. They are interested in public safety. So they want to make sure that the structures, when they are designed, they are safe for public and also they're convenient to use. And that is the spirit of the code. And then the intent is that if you follow the code provisions or the letter of the code, then that will meet the intent or the spirit of the code. And that's the confidence that we have on the codes. And if we follow the code, we should get a reasonable or a safe structure or a well-performing structure. But that now we know that that's not always the case. And then we have discussed in earlier webinars why that is not so. Modern codes, they ensure safety through, like I said, estimation, first of all, of the hazards on load levels. That's the first thing we do. Light load, wind load, they estimate based on the maps, based on some tests data, mostly statistical. Then they prescribe limits on the structural system, members and materials that we can use, size of the column, size of the beam, frame, and so on. Then they define procedures for analysis and design, linear procedures, response spectrum procedures, and sometimes, even nonlinear in some cases. But they clearly define what procedure we should use for what height, what type of structure, in which zone, and so on. They also provide rules for detailing. That's extremely important because connections and reinforcement detailing is finally what gets built on the site. So there are rules governing that detailing, which are also intended to safeguard the structures against poor performance. And then they provide specifications for construction and monitoring, for example, material spend, how to monitor the construction, and so on. And then the intent is to reduce the vulnerability and years of safer structure. So that's the framework of the building code or building codes, mostly towards safety. Now, if you want to design a new building for seismic conservation, what we will need to do is to follow something like that. So we will need to select first of all which code we're going to use. Let's say we are talking about ASC and the ACI group. Then we select the structural system, frame, shear wall, combined system, and also on. Then we select the detailing level. Is it going to be the normal detailing or detail or confined detailing and so on. And then based on that, we will select the design risk way, the spectral explanation, the R factor, omega factors, and other similar factors in other codes. And then we created mostly a linear model. Then we run the model, design, and then we complete the detail. So that's roughly how a new structure will be designed and built. And the most important factor here, which will govern everything for earthquake, is the selection of these factors. The spectral estimations of the seismic zone in some codes, the design based earthquake levels, the R and omega factors, and so on. And we talked about them in a number of webinars before. So let me just remind you that for AASC and ACI and other codes, the design level is set at roughly the yield point. Wind loads are elevated to that point by using the load factors, and the seismic load is reduced from the MCE or the maximum critical earthquake down to the DCPDE, design basic earthquake, which is roughly 2/3, and that is further reduced to the design level by dividing it by R. So that's where we get these reduction factors from the codes to reach a design level. And then we have the true performance of the structure, which may start to yield somewhere around the design level, somewhere around above, and then go up and then plateau and then create that nonlinear response. And then the top of that will be the omega factor, which is the difference between the assumed design level and the actual maximum capacity coming from various factors. So this produces a gray area in this fit because the R ranges from 1.5 to as low as 8, and similarly omega really changes. So this gray area is really gray in the sense that depending upon what factors we choose, we could be anywhere. And so this is the starting point of the problem that we highlighted before also. But for the new structure, it's fine because we follow these consistently and we should get a reasonable structure. Now, let's come to the detailing. In ACI, group of codes, there are three definitions, for example, for a frame: the ordinary moment resistant frame, the intermediate moment resistant frame, and the special moment resistant frame. And the detailing rules are very different, each one of them. Now, the interesting thing is that just because you choose one of those frame types, your R factor can change from 3 to 5 to 8. It's a huge variation just because you choose to follow a certain detailing, whether it is followed in size or not. But if you select one of those, your R factor can be greatly different. So your base shear or the shear or the moment, design moments will be very different, 2.5 times between 3 and 8. So this is a huge difference, and depending upon how we make the choice, the results will be very different. In fact, recently in AIT, we conducted a research on comparing what is the impact of choosing different R or different detailing for a particular structure. So after we have selected that, then we have the capacity and demand ratio that we compare after doing all the analysis and design and everything. And then if the capacity is more than the demand, then we are satisfied. We look at the VC ratio, and then we say that this portion is safe, the green side, and then the right side, or the orange side is unsafe. So that normally we put the limit of 1, and that could be, it's an arbitrary, kind of an arbitrary limit. This could be for moments and shear, or it could be for displacement, rotation, and so on. So that's how we define the safety of a structure using the conventional design codes. Okay, so if we follow that, then if we take the new building, and I'm just going to go through quickly the cycle. So we create a structural system, select the structural system, we create a structural model from there, let's say recap, and then from there we create a management model from structural model, then we create the analysis from there. From analysis, we come to the reinforcement calculation at each location, repars are computed. Then from that, we calculate, we generate the details, and we decide that it's going to be a moment resisting frame, ordinary, special, and we put the detailing, as I showed earlier, following one of those rules, and we get the construction model ready to be constructed. Now, the problem in this one is coming in this zone here, because after we calculate the reinforcement, and by the time we provide the detailing, we round off many things. We group them. Okay, so I was saying that if we create a building structure and then we run it through, we can calculate the reinforcement accurately based on the analysis. But that reinforcement that we calculate doesn't get built because on the way, we have to group the beams. We cannot have every beam to be different. We cannot have every column to be different. So we group them together and we round off and we follow the detailing rules. So what gets built is not what is designed. So whatever R we use, whatever seismic forces we use, they are correct up to the analysis. But after the analysis, from design to detailing, the results are kind of sort of breakout or mixed together, and the final output will be not the same as the analysis would indicate, because analysis would indicate each column at every floor to be different, but detailing will say no, 10 floors are the same, next 10 floors are the same. And that produces a structure which is different from what we designed, and now the best of the structure will not be what we started with. So that brings us to the existing buildings, because existing buildings have been made in a number of ways, following different construction companies, sometimes designed, sometimes not designed, different designers, different building codes over the years. So existing buildings in a typical city, they're spanning 100 years, 50, 70 years, they will be of varied quality and varied capacity. So how do we know about these existing buildings? And when an earthquake strikes, we see that many of them collapse or damage extensively, either fully or partially. So immediately the public raises the question about these buildings, that how do we know if the buildings are safe for the next earthquake? What kind of deficiencies they may have? How can we fix them if they are deficient? So these are the questions that arise immediately after the earthquake. Recently, we experienced in Bangkok, and every building and every resident had the same question. Can I go back? Can I use it? Are we going to fix it? I see a tag there. What does that mean? So, which means that the safety issues come up. And it is very important that we have safe structures. And that is because of the disaster prevention, primarily, because we want to make sure that there's no disaster after an event. We take the earthquake, maybe a strong wind. So and then disaster components that we have seen before. The most important one is the vulnerability, because we can't control the hazard so much. Exposure is depending on the growth, urban population, planning, and so on. But vulnerability of a structure is entirely structural engineers and architects' domain. So if we reduce the vulnerability, we can reduce the disaster risk. So that's the intent. That's why we need to make sure that the structure is actually safe. So let's look at this vulnerability issue. Now, the vulnerability can come from many reasons. First one is design is deficient. Somehow the design was not done properly. The engineers were not well informed, or the code wasn't proper, the software wasn't good. Whatever happened, it was not constructed properly according to design. The structure is just becoming old, it's aging, deteriorating. There's no maintenance. The codes have been changed, the hazard levels have changed. We've seen in many countries that the seismic maps keep revised, and the way that we look at the seismic hazard from the UBC 97 to the current has completely changed. So that means the hazard levels have actually changed because we have more knowledge about hazards. Change in use. We changed building from residential to office, or office to residential, hotel to this, or something like that. That also makes the structure more vulnerable because the demands are different. Post-event assessment. After an earthquake or an extreme event, buildings may have been damaged or may have undergone some damage, so we don't know what the current status is. And then we just want to improve the resilience. Many companies or many clients, before they occupy a structure, they want to make sure that it's going to be safe. So they want to evaluate the resilience of the structure, which is beyond just the strength or safety. So these are some of the reasons why we need to evaluate the building for vulnerability. Now, existing buildings, the question is, will they be safe? What is the performance or capacity, and how we can improve it? But now remember that everything that we did for a new building does not apply here anymore, because we cannot use the design code we use for new building. We cannot select structural system anymore. It's already selected. It's already constructed. We cannot select the detailing level. It's already there. We can't change it. We also cannot select EV, SR, and so on arbitrarily, because the actual structure may not be what we want to build. And then we also cannot use the linear model in most cases. And we cannot move the design and detailing anymore. So the new building design procedure cannot be applied on the existing buildings to evaluate and say this is okay or not. We cannot use the BC ratio concept just to say this building is no longer good based on the current code, because most buildings may not qualify because the codes have changed. And also because the factors were not selected appropriately. So for that reason, we can't force the existing structures to conform the design code for new building. That's the misunderstanding, that we evaluate the existing building and say, no, this is the latest code, this building I'm going to evaluate and should satisfy this code. That's not going to work. That means we have to change the buildings every 5 years when the new code comes in, which obviously cannot be done. So we have to have a different way to look at that. And that way is look at performance, not at the BC ratios, not at the design intent, but actual performance. So performance can be defined as operational, immediate, occupancy, life safety, and collapse prevention. So we check the performance at different hazard levels, different performance levels, and if they are okay, we can say the structure is okay. So it's not now conforming to the code. Maybe some things are not according to the code, but as long as the performance is okay, the building is acceptable. And then the collapse level will depend on, or damage level will depend on where the building is evaluated to be. So that's the way that we look at existing buildings. Sometimes now these days, new buildings are also evaluated based on the same procedure before they are constructed, assuming that this is the what we are going to construct. So this performance-based design can also be used for new buildings. Now, this is the how we can link the two together. So the hazard levels and the structural performance can be plotted on the same graph, and we can check the disaster risk for a building by looking at this curve and seeing where the building is on that curve. So which obviously requires now that we go for nonlinear analysis and all of that stuff. So AC 41 is the guideline. There are many guidelines, of course, but this is one of the current guidelines that is used for evaluation and retrofit of existing buildings. So this guideline is typically based on this tiered approach. This is 3 tiers. Tier 1 is just rapid screening. It's like a checklist, and this can be done quickly. The first level, that you have no calculations are needed, such as basic vulnerability checklist is done, whether the building is like this. There's a whole lot of things that you can check, and it's a visual observation. Plus, looking at the drawings, we can complete that. This is initial assessment. This is initial assessment. Second one is deficiency-based evaluation. We do some hand calculations or simple calculations, do some linear analysis, and some dynamic analysis like model analysis. We calculate, we determine, for example, whether it is unsymmetrical or not, and something like that. So we go to the next. If the first level is not good, we go to the second level and do a rough calculation or initial calculation. And that is sometimes considered to be enough to start retrofit. But if the structure is important and we need a detailed investigation, then we go to the advanced analysis using nonlinear analysis. And then that's what we are talking about here today, mostly. So this 3-tiered approach is what ASC 41 recommends. Now, we have to just compare very carefully now what is the difference between a new building design and evaluation and retrofit between ASC 7, 3, and ACI and ASC 41. First of all, objective is different. In the new building, the objective is to meet the code minimum requirements. But for evaluation is to improve performance of the existing structures, not to meet the code requirements anymore. It can't be done. Basis is prescriptive demand DC ratio based. On evaluation is performance based tiered approach, as I mentioned. Seismic demand for the new buildings includes 2/3 of MC, 2% in 50 years. For retrofit, it varies on the objectives and age. It's not the same, it's much less. If let's say MC is 2,500 years for new buildings, for existing buildings, it could be as less as 1,000 or 800 or 1,200. So it depends. So we are expecting that the buildings is existing, the age half the age is already passed. So based on remaining life, we can reduce the demand levels. So that's very important. Detailing requirements are also different. We cannot follow detailing for every column, every beam anymore because we can't make and fix every column and beam, and we don't need to. Because as long as the performance is okay, we just need to improve some detailing somewhere. For design, linear analysis is okay. For evaluation, non-linear analysis may be needed and evaluate efficiencies. Performance levels for new design is implicit, not explicit. Design for life safety, primarily intention is that, but no proof. But for evaluation and retrofit, explicit, immediate occupancy, life safety, and collapse prevention have to be proven. And then trigger is new construction permit is obtained, and then change in use, damage or retrofitting is determined. So this is the typical flow. Existing building, we identify deficiencies, we determine performance targets, we select retrofit options if needed, we evaluate the performance after the retrofit is designed, and then we implement. So first we see the building without retrofit, whether it's good or not. Then we implement retrofit on the model, evaluate again to see whether retrofit works or not, and then we implement. So it's a double evaluation, not just one way, one step to do that. Because we want to make sure that after all of this, the building will actually perform as expected. And this time, we just fix some collapse level and check for collapse, getting all of the factors, and we select some service level and check for serviceability. That means immediate occupancy, life safety, and collapse prevention. They are checked roughly directly without use of any R, omega, or any other factor. So that's the difference between evaluation and design on arbitrary factors. Now, what are the key things that we should evaluate, irrespective of the method used, irrespective of the codes used, irrespective of the structure used? These are the 10 things normally in a structure that matter: stiffness, stability, strength, deformation, drift, ductility of members and connections, joints, damage, minimization, damping, energy dissipation, and exploration. So these are the 10 things that we can check. And if they all satisfy the requirements of a particular performance level, then we say, okay, this is fine. And this is also for the new design. Now, if you look at the structure, these are built from material to structure in that order. So, for example, stiffness is built from material stiffness, cross-section stiffness, to member stiffness, to structure stiffness, and cross-section members are connected by joints to make a structure, and so on. Materials are connected through bond to make a cross-section. So, on the way, we can also look at those aspects: bond slippage, and connection, and joint carrying and joint design. Similarly, ductility is built up the same way: material ductility to structural ductility. And the energy from material level energy, which is the strain, all the way to structural energy that we can evaluate. So we have the build-up of the response from the material upwards to the structure. And all of these KPIs can be identified and linked to one or two of the properties that we can identify. For example, if the stiffness is a problem, then material, section, member, or configuration can be improved. If the stability is a problem, we look at the geometry and the strain. If the ductility is a problem, we look at the material, section, and confinement, and so on. So we look at every KPI and we look at where it comes from. And if we want to change, it's like levers. It's like dials. You can dial various things and bring them to the acceptable level. So this is like a diagram which we can see which are the levers that you can pull or push to get the KPIs or key performance indicators right. If we have a problem with the drift, we can look at stiffness, geometry, and so on. So this is roughly the map for the deficiencies and the KPIs. And auto-fix KPI also the same way. So if the stiffness is a problem, we can add members. If the stability is a problem, add members. And similarly, strength is a problem, strength the section, strength the members, deformation, increase stiffness, and so on. So once again, there are many ways to look at these KPIs. First of all, as the primary indicators, where do they come from and how to fix it if you find the deficiency. So, for example, deficiency in heavy stiffness, flexible frames. We have a flexible frame, we add bracing or infill walls to improve the stiffness. If the strength is a problem, we do the section enlargement, maybe using various types of strengthening, cross sections and strengthening. Ductility is a problem, we improve detailing. Damage is a problem, we repair and protect. So, this is just some of the, there are many other things that we can do. Just quick example on how we can create a matrix of efficiency versus value. And the most important point that I want to make is that when we do the retrofit, we should try to go from global to local, because we must attempt to find a global solution for the problem before finding a local solution. And the reason is that if you fix the global issue, all of the local issues will disappear. But if you don't fix that, you have to fix every member in the structure. For example, if the cross section of the material strength was not enough, and concrete strength somehow was not enough for any reason, and you want to now fix that problem at the material level, it's going to be very difficult. You'll have to retrofit every beam, every column where the material is used. But if you add an external frame to the structure, for example, and take the load away from the structure, you don't have to fix anything. And the load demands will be reduced. So the global retrofit will almost always be more efficient than the local retrofit if you do it the right way and find the right global retrofit. And there's so many available DRB, for example, external frames, for example, and so many things. Dampers, for example, even isolators. In Philippines now, a lot of buildings, they're finding it that just by cutting the whole floor and at one level and putting isolators fixes every problem in the building in all of the floors above, because you just reduce the demand completely. So there's no need to do anything. So that's the quick fix for the whole structure at one time. So that's what we should be thinking about. So global deficiencies, for example, soft story, weak story, torsional irregularity, vertical irregularity, we can look at all of them by adding mitigation strategies like bracing, jacketing, adding more resisting elements. So this table, I don't need to repeat what's written here. You can look at it later when we share this video. And then you can see that soft story, we can fix like that. Weak story, we can add, increase the strength through jacketing and so on. And torsional irregularity, we add walls to make it balanced. We add frames to reduce the irregularity. We can look at the model response and so on. Vertical irregularity, same way, we can strengthen the peak levels and add walls or remove walls which are causing the problem. So you can see here that the deficiencies at global can be fixed in that way. But most of the time, they will also fix local problems. Local deficiency, however, can come from short column effects, which means the sub-column is blocked by partition walls. So we need to remove the partition wall or put a gap between the partition walls and the column, because a lot of failures come from the short column effect in many low-rise buildings, because the partition walls going only halfway, they cause the large shear in the column because we remove this short thing. So that can easily be fixed by making sure that the partition walls do not hit the column and cause that impact. Similarly, weak column, the strong column coalition. Normally, column should be stronger than weak, but sometimes in the low-rise building that's not possible. So we have to do retrofitting of columns, or we have to make sure that that particular frame does not participate in the lateral load resistance. Inadequate joint detailing is, most of the things you repair a joint. Once again, the one way is to strengthen the joints, another way is to reduce the demand of the joint. And similarly, for reinforcement language, we have to fix that to local development. And similarly, unreinforced infill or cladding, that causes a lot of problems. So we can either make them, improve the strength of the masonry by adding some plaster with the mesh or jacketing of the wall, and so many things can be done. Or we remove them from the system altogether. And a lot of the time, the last problem is the most common one, that the buildings have never been designed for seismic loads. They were designed for gravity loads. They were designed before the codes became aware of these things. So then we have to go back and add basing and add mostly external retrofitting. You can't fix the building by local retrofit. So if you go to many countries, for example, in San Francisco, you will find a lot of buildings with external frames, with BRBs added to them, because it's not possible to fix a very old building through local retrofits. So this is a kind of a total matrix of various retrofitting strategies versus their effect on the KPI. So if you look at this one, it's just a guideline, just telling you that if you do this one, you will improve stiffness, this and that. If you do this one, you improve that. And this table is a good starting point to choose the right retrofit strategy for the deficiency that we find. Some things are helping in everything. For example, BRBs, they are really good. They help in so many things. So these days, adding BRBs is a very common solution to most of the retrofit problems. Of course, if you add, other similarly energy dissipation devices, they also can help. So the third tier is a detailed evaluation of the structure using full nonlinear models. Whether we do Kushner analysis or dynasty analysis, it depends on the information that we have. But typically, a nonlinear model will be sufficient, and that's what Dr. Naveed will talk about in the next 1 hour. And so, if we want to satisfy the third tier, we need to ensure that we have the 3 performance levels met: immediate occupancy, life safety, and collapse prevention. They are explicitly checked. And there are guidelines, there are limits on everything, there are procedures they are given there, but it will obviously requires far more work than designing the building. So with that, I will just end here. Thank you so much.